Hello everyone, welcome to the second part of the Vision and Language session. I'm Xinlei Chen, a research scientist at Facebook at Research Menlo Park. And in this tutorial, I'm going to cover the story of visual representations for vision and language tasks. So let's get started, and here is a high-level overview of the standard pipeline that people have built for vision and language tasks. Since it is a multimodal problem concerning both vision and language, we usually build a visual representation out from the vision side and build a textual representation from the language side. And then there will be a third multimodal fusion model that takes input from both sides and output things from there. Here is a typical example of a vision and language task called VQA, Visual Question Answering, where the input is an image from the visual side and a question in the formal language. And then the model is expected to give an output, in this case also in natural language, that correctly answers the question. It is easy to fit the pipeline we have previously shown to this VQA task. During inference, it will first compute a visual representation specific to the image and a textual representation for the question, and then feed both of them into the fusion model for reasoning. And hopefully it will find the correct player that takes the shot, find the corresponding location where the number is located, and then read out the answer 14 here. So, given this process, you can probably tell that the most interesting and exciting part of vision language research is on how we fuse the two types of the representations together and do joint inference in a reasonable and intelligent way. And in fact, this is what most of the vision and language tutorials are talking about. However, it is also worth noting that the choice of input representations can also play a significant role in the model's performance on such tasks. So that in this context, this tutorial, we would like to do it a bit differently and focus on the story of visual representation in vision and language tasks. To motivate a bit further, there are two reasons why we want to cover this in the visual recognition tutorial. First, it is actually a great example of how visual recognition tasks beyond ImageNet classification, for example object detection, can serve as an engine for other downstream tasks. And second, following the breakthrough in NLP, these days vision and language pre-training is very popular, where a BERT-like model will be first pre-trained on some large-scale vision and language paired data, and then the pre-trained representation is shown to be useful for specific vision and language tasks like VQA or visual common sense reasoning. While this trend is exciting, many approaches just focus on pre-training the joint fusion module and build on top of existing pre-trained and fixed visual representations. We hope this tutorial can raise more awareness of the full picture of the pipeline and encourage more great works in this direction. The tutorial will be divided into two parts. First, we will give an overview of the story from ConvNet to bottom-up attention-based visual representations. The latter is also known as region features for vision and language tasks. Second, we will cover our recent revisit of directly using convolutional grid features for vision and language, where we conducted controlled studies to compare region features and grid features and share some insights. Note that we'll be using representations and features interchangeably in this tutorial. Let's dive into the first part. The story started from year 2014, and at that time ConvNet has just begun to show its power, and people have just started to explore its representations for vision language. The features are quite basic, but because neural networks can already embed both vision and language into a learnable latent vector, this unified view offers some great improvements for tasks like image captioning already. And typically, one would like to take a pre-trained network from the ImageNet classification task. Because it is trained on classifying object classes, intuitively it could help high-level recognition tasks or reasoning tasks like vision language. And for backbone, one can choose AlexNet, VGG, or GoogleNet, as they have already shown good performance on ImageNet classification and are publicly available. When it comes to layers, the last FC layer right before classification usually gets picked because it is considered to be most semantically meaningful without being too biased into ImageNet 1000 classes. But then, as the research developed, people realized that single FC layer may not be enough for vision and language. Intuitively, as questions and captions are structured, they usually mention multiple objects and their interactions. So a single vector may not be rich enough semantically. But more importantly, those multiple objects and interactions usually occur in different places and spatial locations in the image, and it is really not ideal to represent all of them into a flattened vector that could potentially mess up spatial information. And at the same time, another important technique called attention mechanism has emerged from machine translation and getting into vision and language research. Given this new technique, the fusion model is becoming stronger. It is better at capturing relevant portions in the visual features by paying attention to those portions. As a result, one can feed in more redundant and less compact information into the fusion model and just let the attention mechanism to figure out what is the best way to use that information. So these two drove the next step of development for visual features used in vision and language, convolutional grid feature maps. While conceptually simple and nowadays widely accepted, grid features offer nice properties to overcome the drawback of the single vector representations. There are a set of multiple features for a single image, and all of them are spatially localized in a grid. While some features may not be informative for questions and therefore redundant, the model can actually leave the fusion or attention module to pick the salient features given any top-down signal. So in the previous example we have seen, given the question, what number is taking the shot, this question can serve as a top-down information to help the model to attend to relevant grid features for answering this question. And getting grid features from ConvNets is easy. At that time, ResNet was first proposed and shown superior performance compared to all previous ConvNets in visual recognition. Therefore, it became the standard choice of the backbone. And when it came to the choice of layers, the last convolution layer becomes a natural choice. And because it is the ConvNets we are talking about, even for networks that end up with FC layers, it is easy to convert them and the previous FC layers into a convolutional kernel that produce grid feature maps when one enlarges the input image size. For ResNet, it is even more straightforward as only average pooling is used before classification, taking the last conv layer output is effectively the same as taking the last layer after pooling. Then we fast forward to the year 2017 when bottom-up attention is proposed. The central idea of bottom-up attention is to use bounding box or region-based features for visual representations. Just like grid features, it uses multiple spatially localized features to jointly represent an image and overcomes the drawback of single vectors. It is named bottom-up because the regions are selected without top-down input from text side and are only based on image pixels from bottom-up. This idea is in fact not new. Back in 2014 or 2015, people have already used a set of region features pre-trained on ImageNet object detection to represent an image for captioning. In 2017, deep learning-based object detection are way more matured, and Anderson et al. Really nailed down the crucial details and successfully made it working. Thus, this idea of using region features for visual representation is popularized as bottom-up attention. How is bottom-up attention implemented then? It is quite simple. First, it pre-trains a fast RCN object detector on visual genome annotations, using a ResNet with its weights initialized from ImageNet pre-training. The detector is a modified version from the original one that just does object detection, since it also includes another head for attribute classification. This attribute head is important per our analysis for VQA. Then, given an image, the detector does two things. First is region selection, which is fulfilled by region proposal network that picks the top n bounding boxes. Second is region feature computation, where each selected region will pull features from the shared feature map and do some computation to get the representations for that region. And finally, features from all selected regions are stacked together to form the representation for the entire image. On the right, I'm showing a visualization of this process. Note that if you are familiar with object detection, this kind of design is called C4, as it runs the entire C4 block of the ResNet for region feature computation. Bottom-up attention has won VQA 2017 challenge, and ever since its proposal, the region features have dominated the leaderboard to date. Then we are curious to see what makes it successful. Well, intuitively, region features do have a set of advantages over grid features. First, it localizes individual objects better, whereas grid features can only give a rough idea, especially when the feature map is coarse. Second, it is flexible in capturing both coarse and fine details in the image. And thirdly, modeling regions also allows it to easily characterize the interactions between objects, for example, when the objects overlap. So, are these underlying reasons for its success? Unfortunately, you could probably tell that multiple factors have actually changed for it to have controlled comparison with previous works. For example, in bottom-up attention, the weights are not only pre-trained on ImageNet, but also on visual genome for object detection and attribute classification. Therefore, a controlled study is needed to understand the behavior better. Our recent study is such a work to fill in the blanks on bottom-up attention features. It is led by our intern Huaizu Jiang as part of his internship at FAIR. As you can probably tell from the title, we find the grid features can surprisingly match the performance of regions and offer some advantage in addition. Let's talk about the studies next, and this is going to be the second part of the tutorial. Here is a list of our basic fixed setups for the controlled study. Specifically, we fix pre-training task and dataset to be visual genome object detection plus attribute classification. We fix a backbone and input size to be resonant 50 and 600 times 1000, which are pretty standard for analyzing object detectors. We also fix the evaluation task and the metric to be VQA and its VQA score, which is a variant of accuracy. And finally, we fix the VQA model to be Pythia, which is lightweight and helped us win the VQA challenge in 2018. Given the basic setup, the first study is to directly check the most naive way of converting the region features to grid ones. Here, minimum amount of change is our friend, as this can give us the fairmost comparisons. So what we did is to use the same training setting for fast RCN and only convert the detector back to a normal resonant classifier during testing time. Specifically, we feed in the same input image with the same processing and use the same layer, which is the last convolution layer of ResNet, to extract grid features. The H by W number of grid features are then used to jointly represent the image. The results are summarized in this table. The first row is showing the region feature baseline, which is 64.3. The second one is our grid features by directly converting to ResNet classifier and take the same layer. And the third one is a prior grid features pre-trained on ImageNet. We can see that the resulting grid features are almost working out of the box, given a VQA score much closer to bottom-up region features than prior grid ones. This is our first evidence that grid features have the hope to work as well as regions. Now, after training, we still convert the modified fast RCN detector to a resonant classifier for feature extraction. Note that the feature extraction setup is exactly the same as the previous study, which means we do not include the additional 2 FC layers or use dilations, and still get the H by W grid features. Here is the result of our second study, where we copied the first 2 rows of previous table and added 2 additional rows for our 1 by 1 ROI pool setting. We find this design hurts object detection performance and the correlated region feature performance on VQA. But on the other hand, it helps grid features to perform better on VQA scores. One intuitive explanation is that since using a single vector to do object detection is a more challenging task, the grid features in the backbone are trained to be stronger and more representative. Overall, these two studies deliver the main message of our paper. Grid features can indeed work as well as region features for the VQA task. We show some visualizations for the top-down attention map here for our baseline region features and our improved grid features. The brighter the overlaid mask is, the higher the attention values. We can see that while regions and grids attend to different portions of the images, both of them can provide semantic and spatial cues about what and where the model should attend to, and both can lead to right answers. We also show some failure cases, and it seems the attention maps are pretty reasonable even when the models fail. Interestingly, sometimes grid features can look at precise locations, whereas the region features are missing it due to lack of bounding boxes that supports the evidence. This is the case for the bus number on the top right. Our findings are generalizing quite well. Beyond the basic setups, we also tried different backbones, different VQA models, for example, also the 2019 VQA Challenge winner MCAN, different VQA tasks, for example, with dataset that focused on blind users, and different other tasks like image captioning. And on all of them, we find grid features and region features are similar in performance. Please see more details in the paper if you are interested. We participated this year's VQA challenge based on this finding. There, we further improved pre-training process. For example, completely removed the bounding box regression loss in the second stage of fast RCN. Here, we are showing the results of best single model performance progressed over the years. We are pleased to find our grid features can achieve very strong results and winning the VQA challenge this year. We have released all the code, pre-trained models, and grid features in the link below. One may wonder, why our grid features can work so well. We find the two most important contributing factors are pre-training task and image input size. For the first, we have already shown that VG object plus attribute detection offers more powerful features over vanilla ImageNet pre-trained ones. And for the second, we list three settings to accommodate the difference in common practice for image size preprocessing in classification and detection. The two underlined scores are the baseline numbers we reported before. We find input size matters quite significantly, and our VG pre-trained grid features can further improve the VQA score if we feed a larger image size. As a final study, we also varied the attribute loss weights when training the fast RCN detector from 0 to 1. We find without attribute, the model performs worse, likely because VQA models need to address object attribute related questions like what color is a hydrant in the image. So, why our findings are interesting? Beyond gaining insights of the button-up attention features, we also believe revisiting grid features can offer two major benefits. First, for science and research, it simplifies the pipeline by removing region-based components in the visual representation part of the model. Now, the features can be obtained by a single forward pass of a convnet. This can also potentially make end-to-end optimization of visual representations easier for vision and language tasks down the road. Another practical benefit is speeding up. Without region-related computations that can take up to 90% of the computations, grid features offer significant speedups to all the models we have tested. This lightweight pipeline also allows visual features to be extracted online, and enabling explorations of early fusion models between vision and language. For example, we have a recent work that specifically targeted visual counting questions led by our AI resident Chen. Interestingly, we find the high coverage of grid features offer an advantage for counting, and applying modulated convolution is already helping us achieving state-of-the-art.